Swayam Prabha. Digital India. Educated India.
Welcome to Module 1, Lecture 2. We will follow up from where we stopped last time, but generally we will be following this time structure of cement compound. Then we will look at structure and hydration, the main chemical reaction, hydration process and bonding action. So, we will be looking this time to structure of cement compound after briefly looking at where we ended last class. We will look into hydration product and their structure, main chemical process of hydration and the bonding action. Remember last time we looked into schematic representation of the formation of hydration of Portland cement. We said that we start from element oxygen, silicon, calcium, aluminum and iron, which forms oxides, calcium oxide, SiO2, silicon oxide and aluminum oxide, that is silica and alumina, aluminum oxide and iron oxide. Then this follows from the oxides the compounds of cement, and they are C3S, C2S, C3A, C4AF. All this combination gives us Portland cements of various type, and when hydration occurs in presence of water, it gives us two products CHS gel and calcium hydroxide. So far we have not looked into this. So, last class we stopped somewhere there and we talk of also just the heat of hydration. We said that out of all these compounds, C3S produces 500 joules per gram, C2S 260 joules per gram and C3 867 joules per gram and C4A 419. Corresponding calorie per gram is also given side by side. So, this is what we looked into in the last class. Now, we will follow in this class. So, we look into structure of compounds of cement. Now, you see silica Si, silica, Si silica belongs to same group as carbon in periodic table, in same group. And if you recall that they have 4 electrons in their outer shell, and this silica generally, this silicon therefore combines with 4 oxygen, forming SiO4 ion with 4 negative valency. So, since it has got 4 electron, those 4 electron can combine 4 oxygen covalently, and this will have, it will be SiO4 4 negative ions. Silica is SiO2, we know that silica is SiO2. So, this has got a tetrahedral structure with SiO4, right, and Si covalently bonded with 4 oxygen. This is the basic repeating unit in structure of silica and silicate. So, that is the fundamental. Now, you know, cement is calcium silicate, tricalcium silicate and dicalcium silicate, etcetera, we have seen. It is also aluminate. So, first we are trying to look at the silica structure. So, silica has a tetrahedral structure like this. The silicon here, there are 4 oxygen atom, they are covalently bonded with silica Si silicon atom, and it is 4 negative, it has got 4 negative balances existing. It can 4 negative balances exist in this one. The structure of silica therefore is something like this. The blue one is the silicon, with the red ones the oxygen. Here of course, the yellow one is the silicon and this 4 are the oxygen. So, you can see that they repeat itself, and each oxygen is combined with 2 silicon. There is one silicon here, another silicon here. Each oxygen is combined, it combines with 2 silicon, and this process repeats itself, and therefore, with one silica, one oxygen, half of it is connected to a silica and half is connected to another silica. Therefore, each oxygen is connected to 2 silica. So, if there are 4 of this one, 4 of the oxygen combined with 1 silicon, since oxygen combines with 2 silicon each. So, therefore, structure of SiO2 would be repetition of this tetrahedra. So, this tetrahedra on repetition forms SiO2 or compound silica. So, in silica it is a 3D network of tetrahedra formed with oxygen bonded to 2 Si. So, this is the SiO2 structure or silica structure. Crystalline quartz is one of the silica. Crystalline quartz, one of the most stable silica. The tetrahedra are arranged in 3-dimensional periodic pattern. This in crystalline quartz, the tetrahedra, this tetrahedra SiO4 with 4 negative bond available is arranged in 3-dimensional periodic pattern, all right. In non-crystalline silica, tetrahedra are randomly bonded. In non-crystalline silica, tetrahedra are randomly bonded. This are randomly bonded. So, this is the silica structure. Now, in cements basically, silica can combine. In cements actually silica can combine with other oxides. In 3-dimensional network of silica, other oxides can be dissolved to yield number of crystalline and non-crystalline silicates. So, in your SiO4 structure, 3-dimensional network, SiO4 3-dimensional network, other oxides can get dissolved, right, and they can combine, and therefore, you can get both crystalline as well as non-crystalline materials as products. So, various kind of silicates you get. Now, cement is one such example. So, cement is the example of such non-silicate. Cement is example of such silica combining with other oxides. Silica in 3-dimensional network of silica, other oxides forms cement. That is why I have got tricalcium silicate and dicalcium silicate. So, essentially you see the silicate structure of SiO4, this repeats, and in between you will have calcium and oxygen atoms coming in and forming the structure of tricalcium silicate and dicalcium silicate. Let us look further into it, more into it. Let's look more into it. Let's look more into it. The structure of compounds of cement. C3S is built up from calcium ion, SiO4 ion, tetrahedron, orthosilica as it is called, orthosilicate, and oxygen ions just being bonded, this is bonded to, this oxygen ions are bonded to 6 calcium ions like this, something like this. This SiO4 tetrahedra are connected by calcium ions. So, in structure of C3S, it is built up of calcium ions, SiO4 tetrahedra and oxygen ions. So, these are bonded to calcium ions and SiO4 tetrahedra are connected by calcium ions. Let us see how it is. Let us see how it is. C3S is also called, its mineralogical name is halite, which you have seen earlier. It is a solid solution. It is a solid solution. So, combining all this calcium, oxygen and SiO4 tetrahedra, but it has also got some minor compounds like sodium oxide, potassium oxide, etc., etc. So, those minor compounds, magnesium oxides, they are there. Generally, it exhibits a polymorphic structure, polymorphic structures, and differs structurally by minor deformations of basic hexagonal structure. So, it has got a basic hexagonal structure. It is polymorphic, not the same crystal structure, polymorphic. The morphology differs, more than one morphology exists, and all this morphology differs from the basic hexagonal structure by minor deformations, all right, by minor deformations, right. So, let us look further into this tricalcium silicate hydrate or halite structures. You see, this has got subshell. If this is, this one are the calcium ions, orthosilicate ion, that is SiO4, this is SiO4 negative orthosilicate ion, oxide ion and calcium ion. They are arranged in subshells like this. So, this is your orthosilicate ion, the calcium ions, calcium ions, and in this one you have got oxygen ions, right, and this combines together to form full shells with subshell A, B, etc., etc. So, halite has got a structure, that is C3S has got a structure of this kind, with small calcium ions and orthosilicate ion surrounding them in the manner as shown. Simplified halite structure, if I look at, that is C2S, which we call, mineralogical name is halite, which you have seen in the last class. So, structure of C2S, that is halite, involves calcium ion and orthosilicate ion and exhibit polymorphism like halite. So, structure of C2S halite, it also involves calcium ion, orthosilicate ion and exhibit same polymorphism like halite, but obviously the structure should be different. Halite also of course is solid solutions containing minor quantities of other oxides like sodium oxide, potassium oxide, alkalis and magnesium oxides and so on. So, the mother compound, other minor compounds are there in small quantities in halite as well, So, this also is a solid solution. Minor quantities of other oxides are present in structure of halite as well. And if we look at it, same, it will look like this. This orthosilicate ion is here and this is the calcium ions with orthosilicate ion placed like this. So, this is the structure of C2S. If we look at structure of aluminate, it has got one difference, it does not exhibit polymorphism, right. So, does not exhibit polymorphism. It has got a cubic structure of Al6O18 with ion with 18 negative valency. So, cubic structure is built from calcium ions, it has got a cubic structure, the aluminate, cubic structure built from calcium ions and ring of 6 Al4 tetrahedra of this formula. Let us see this one. If this is oxygen and aluminum, Al6O18 tetrahydra is something like this. The oxygen is here connected to aluminum, smaller aluminum. So, 1, 2, 3, 4, 5, 6 of them should be there, 1, 2 and there should be 6. So, Al6 with O18, 6 Al with O18 are connected in this manner, forming Al6O18, right. Structure is something like this. Now, this is connected to calcium ion, this is connected to calcium ion in case of aluminate. So, unit cell actually is composed of 64 subcells, out of which 8 are occupied by Al6O18 rings, and calcium ions are they occur at the body center of some of the remaining subcells and corners of the other. So, aluminate structure is of something like this, right. Aluminate structure of this, well, it has got Al6O18 rings, it has got Al6O18 rings. Calcium ions occur at the body centers of some of those subcells, and in case of some of the other subcells it occurs at the corners. So, 64 subcells are there. So, essentially calcium ion and Al6O18, the rings of these ones are there, and calcium ions are placed at the body centered position for some of them, and remaining subcells, and for remaining subcells it remains at the corner. Structure of ferrite, if I look at it, it has got calcium ion, AlFeO4 tetrahedra and FeOlO6 tetrahedra, and looks something like this. These are the calcium, blue ones are the calcium, the red triangles are the AlFeO4 and FeOlO6 are the ones of this kind, black ones are the FeOlO6. So, they have a structure something of this kind. So, that is how the structure of compounds of cement or the halite, baelite, aluminate and ferrite looks like. Now, what is important for us from this point of view is one feature which is common in all this structure is that large anions are bonded with small size cations, calcium cations. Your cations are calcium, anions are SiO4 minus 4, Al6O18 minus 18, etc. So, you can see the sizes of these anions are very, very large, cations are small, calcium cations. So, this is one common feature, and this has a role in its chemical reaction with water. All right. So, this is one major feature, common feature for all these chemicals, which is important from our point of view, is that it has got small cations, that is calcium ions, with large anions. We of course know that it is difficult to identify these individual minerals in the cement through conventional technique. If you take cement by conventional technique, it is difficult to identify these chemical compounds. You can't just separate out one from the other, they are all together. Now, this when mixed with water or comes in contact with water, it reacts. Let us see why does it react. The purpose of discussing about the structure is, the structure has a role in its chemical reaction with water. We call this reaction as hydration, but in general hydration is a term used, is a process of formation of hydrates. It is used in the context of process of formation of hydrates. Hydrates are salts or compounds associated with water of crystallization. So, hydrates are salts or compounds associated with water of crystallization. That means, cement when it comes in contact with water takes water of crystallization and becomes hydrates. Therefore, we say hydration of cement. That is why we say hydration of cement, hydration reaction of cement, right. Hydration is a general term used in chemistry. This, why does it happen? Why some of the ions, some compounds exhibit or chemically combined with water to form hydrates? Well, because anions are too large compared to the cations, to the size of available cations, such that the packing efficiency of the compound will not come within the range of required stability. You see, cations are small, anions are large. Cations are arranged with the anions in some manner. Now, if the size are too small, they do not pack with appropriate packing density. Now, what is packing density, which we will talk about later on also, is the volume of solid divided by volume, total volume, volume of solids divided by total volume. So, the cations and anions must pack such that they occupy 64 to 74% of the volume to have a stable structure. When cations are small, anions are large, the space between the anions are not filled completely by the cation, therefore, the packing density is not the stable packing density. And when you do not have a stable packing density, they actually take water. Well, cements belongs to this kind of compounds, because your cations are small, calcium cations are small and calcium cations are small, and these small calcium cations with large anions, the packing is not a stable packing, packing density is not stable. And in such situation, what happens? To achieve this required packing efficiency, the unstable compounds incorporated water of crystallization within their structure in order to fill the space left around the cation. So, to achieve this required efficiency, these compounds where cations are small, anions are large, they incorporate water of crystallization within their structure in order to fill the space left around the cation. And cement is like this, right? Cement is like this. So, cation is then artificially enlarged, so that stability is achieved, crystallization occurs, stability is achieved, right, by crystallization. So, cations is then artificially enlarged. So, therefore, you can see that why cement readily take water and react with water. It takes quickly, it gets hydrated because its cation sizes are small and anion sizes are large. Therefore, it can readily take water and react with water, and water of crystallization and hydrates are formed. Hydrated water has got the property that it is chemically bound. It is chemically bound in the structure and therefore, not available for process such as fungal growth. This water is not freely available, this water is not freely available, it is not available for fungal growth, it is attached chemically, right. So, it is not available for fungal growth. You want to remove this water, high temperature is required. High temperature is required to remove this chemically bound water of crystallization from the structure, because it is now chemically bound. So, you can't remove them so easily. So, you have to heat it up, supply a lot of energy to detach this water out from the system, out from the hydrated system, right. This water is also not physically detectable by a moisture meter. That means, it does not, you just can't measure them, simply it is a part of the solid system. And if you put a moisture meter like let us say electrical conductivity etc., this is not readily detectable by any kind of moisture meter that you have. It will not evaporate. If you heat to 100 degrees centigrade, it will not evaporate, because it is much more strongly bound than the free water. Ions are usually formed from covalently or ionically bonded structures, right, and compounds of cement have large anions with small cations, thus high affinity for hydration. So, that is what we have understood, that in cement we have got large anions and small cations. So, that readily hydrates. That is why it readily hydrates and form the hydrated structures. So, that is why the structure of cement compounds were important, because to understand that their anions are large, cations are small, and therefore, they can readily hydrate, and it is therefore, we now understand also process of hydration, and that is why cement reacts. Now, main chemical reaction, if you look at it, we abbreviate, like we abbreviate calcium oxide as C, water we abbreviate as H as we mentioned earlier, water is abbreviated as H. Thus, calcium hydroxide will be written as CH, calcium hydroxide will be written as CH. So, C3S reacts with 6 water, 2 C3S reacts with 6 water, this is the typical reaction, forming calcium silicate hydrate, the water goes into the calcium silicate structure and calcium hydroxide. So, it produces calcium hydroxide and the calcium silicate hydrate. Similarly, belite or C2S also reacts, forming calcium silicate hydrate and calcium hydroxide. One can note this, that it produces more calcium hydroxide, C3S produces more calcium hydroxide than C2S. 100 grams of C3S reacts with approximately 24 grams of water to produce 75 grams of CS, C3S to H3 and 49 grams of CH. 100 grams almost reacts with 24 grams, producing 99 and 22 grams of calcium hydroxide. So, these are the two most important reaction. Now, this is there is a reason why we call it as a CSH rather than compound complete formula. We will come to that shortly. This has got a gel like structure and this is responsible for bonding. So, this has got a gel like structure and responsible for bonding. We will come to that in more details. The next chemical reaction, important one, is of course, C3A reacting with 6 water, forming calcium aluminate hydrate C3A H6. This is the typical reaction. But one more reaction which is important is reaction of C3A with calcium sulphate with water of crystallization. Now, what is this? Calcium oxide and SO3, because SO3 is abbreviated as bar and then 2H2O. So, this is nothing but CaSO4 2H2O, gypsum. This gypsum is added to the cement, as we have mentioned earlier, that gypsum is added to the cement to control setting. In the last lecture, we talked about that. Now, this calcium sulphate or gypsum, hydrated calcium sulphate reacts with C3A, readily reacts with C3A and forms a compound of this kind, C6A aluminum oxide, S3 bar, that is SO3 and H32. So, C3A reacts with gypsum in presence of water to form this kind of a compound, and this is called ettringite. This is called ettringite. There is a name ettringite. This is called ettringite. So, this reaction forms, but this is not a very stable compound, and later on it changes in presence of C3A and water to what is called monosulfate, to what is called monosulfate, S bar only, not S3. So, this is called monosulfate. So, these two reactions are also important in case of hydration of cement. Earlier two reactions and this alumina reactions we have seen here. So, these are the main chemical reactions for cement with water. Gypsum control setting properties, we will discuss this sometime later on. What happens is, if you do not have gypsum, then C3A quickly reacts with water and can result in what is called flash set, and too much of gypsum on the other hand can result in what is known as false set. We will come to that. So, C3A AHC cubic crystalline, and the reaction is rapid, leads to flash set of cement as a whole, and it is not desirable because this flash set do not allow C3S and C2S to react. It quickly solidifies kind of at a very short period, and it is not desirable because other reactions do not continue. So, flash set is not desirable, and that is why we add gypsum in the cement. Now, gypsum essentially delays the reaction by forming a trangite layer on surface. Setting takes place by formation of CHS later on. So, this is what it does. Gypsum, it delays the reaction, right, by forming a trangite. We will look into this somewhat in more details from time to time, and setting takes place by formation of CHS. Too much gypsum is also not good. Too much gypsum is again not good, because it results in what is known as false set. It results in what is known as false sets, like sets like plaster of Paris, because gypsum itself will react with water and form hydrated gypsum, like plaster of Paris, and therefore, this is also not desirable. This is called false set, but you can actually remix it a little bit and it will set again. So, both optimal quantity of gypsum is important. Gypsum should be able to retard the reaction of C3A, so that CHS or C3S, C2S can react, but at the same time too much of gypsum might solidify it by reacting itself with water instead of C3A alone, and thus by giving impression of a false set. So, anyway, this again we may look into this sometime later on. Let us come back to, so we have seen the chemical reactions or reaction product of the cement. These are, we have seen that calcium silicate hydrates. Let us look at their structure, because these structures have some role in their properties and things like that, in understanding their properties and hydration process itself. So, let us look at structure of CHS. Exact chemical structure of CSH is complicated and exhibit variable composition, hence we call it CSH. That is why there is a reason, there is a reason we said that it has got a gel like structure, it has got a gelatinous structure, but we said that we do not denote it by the exact formula, because it has got variable formula. So, we generally denote it by CSH, it is not actually crystalline, as we shall see. CSH is not crystalline, right, it is not crystalline. We will look into it, and therefore, the crystal structure of CSH is not really defined. Instead, we talk of nanostructure of CHS at a very fine level. So, this CHS gels show no long range order, hence largely amorphous. This do not show no long range order, therefore, amorphous. A repetition of the structure is not there, therefore, it is largely amorphous. Several different morphological types of CHS have been identified based on evaluation technique. There are a number of, they have similarity to some of those calcium silicate hydrates, pure calcium silicate hydrates produced otherwise not from the cement, namely tobermarite or similar ones. There are several minerals crystalline structure they have, but the CSH produced from cement, they do not have long range crystalline structure. So, therefore, they are largely amorphous, cannot be associated or cannot be assumed to represent such crystals as tobermorite. So, they are essentially amorphous, right, and the product that you find out, the crystal structure you determine, usually depends upon the evaluation technique. Well, it actually reaction of cement with water results in precipitation of colloidal gelatinous mass, and this forms a network. This forms a network. This forms a network. Cement comes in contact with water, hydration reaction takes place at the surface, and reaction product is formed at the surface itself. So, we have a diagram, we have of course, diagram which I will come to. So, what happens is the reaction takes place at the surface. Cement particles, well, they may be clogged, but if you can disperse them, if they are separated from each other, right. So, the water, when it comes in contact with the water at surface, the reaction takes place at the surface and products are deposited at the surface, because water comes in. Now, next what will happen? The product of course, is colloidal and gelatinous, and it forms a coating on the surface of the cement itself. It forms a coating on the surface of the cement itself, and this coating acts like a semi permeable membrane. It acts like forms a coating on the surface and acts like a semi permeable membrane. Now, on the grain size, on the cement side of this semi permeable membrane, there is more concentration of the solute, that is the cement itself, and on the other side there is less concentration of the solute. So, when you have difference in concentration across a semi permeable membrane, it gives rise to osmotic pressure. We will come to that sometime later on. We will come to that sometime later on when we talk at appropriate time. We know that if there is a difference of concentration exists across a semi permeable membrane, you find that after some time concentration tend to be same. After some time concentration tend to be same, because a pressure difference exists between the higher concentration side and the lower concentration side, and this pressure is osmotic pressure. We will talk about this, because we will be talking about diffusion of chloride into concrete and so on in the connection of durability. So, anyway, at the moment we understand that there will be an osmotic pressure created on the grain size, and that will result in rupture, breakage of the semi permeable membrane, and water will penetrate, water will penetrate into the unhydrated portion of the cement, right. It will penetrate into unhydrated portion of the cement, and thereby hydration reaction would progress. So, concentration of solute is high on the grain side of the gel compared to solution outside, resulting in osmotic pressure, and after induction time, the osmotic pressure ruptures the membrane, that is what I am saying, and water comes in contact with the unhydrated portion of the grain, causing hydration product to progress both inwards and outwards into the voids between the grains. So, this osmotic pressure that is higher on the grain side causes rupture of the membrane, and thereby water can enter into the inside through the membrane to unhydrated cement, and reaction product will be formed inside, both inside, some of it will go outside and actually get deposited into the vacant space that is available, and also within the space where original cement grain, outer periphery of the original cement grain itself. When product between each grain merge, so when they merge together, they will touch each other, the setting would, it will form a solid skeleton, or what we call setting would occur. So, this product we will diagrammatically we will explain this again. So, when this product they come and touch each other, they form the solid network, touch each other, they will form the solid network with of course void space inside, and that time when the solid network has formed, it is actually we call it the setting has occurred, because setting is the process of solidification of cement water plastic mix. So, due to the reaction solids would form, they would touch each other and thereby the solid network would form and that setting would occur. Further then process of more generation of solids might take place, more hydration product may form and fill in all the voids that is that is available within the space, right. So, when product between each grain merge, setting occurs due to lack of water as the system becomes closely packed and then hardening would occur. By addition of water to cement, a plastic paste is prepared, that is what we said. Due to chemical reaction, water is consumed and paste tends to solidify. This process is setting. Solid then hardens and gains strength. So, setting is solidification, it does not gain strength at that sufficient strength at that moment, and then gradually it will gain strength as well, it will gain strength as well. What we call the first phase of this solidification, it coincides with chemically dormant period, we call it chemically dormant stage, and complete solidification on formation of definite shape and volume refers to final setting. That means, a solid has got a definite shape and volume. So, when cement and water mixed, when you mix cement and water, it forms a plastic kind of a paste. This gradually solidifies, and when it attains a definite volume and shape, fully solid, we call it final setting has occurred, Well, physical changes, as we can see, addition of water, we get plastic and workable paste. This is chemically we call it as dormant stage, and it then solidifies such that if you disturb it further at this stage, after this stage, then it will lose some of its property. So, that state we call as initial set. It has solidified in such a manner that it is not fully solid, still soft, not fully solid. You can, if you press, possibly you can make a small dent, it is not fully solid, but if you try to disturb it further, it is nearly solid. If you try to disturb it further, its properties will be affected. So, that is what is initial set, generally around minimum should be half an hour and usually could be 45 minutes, right, could be 45 minutes or so. Followed from this is the stiff and unworkable paste, stiff and unworkable paste, that means it has become now fully solid. So, it is stiff and unworkable paste, and that corresponds to final set. As I was saying, now it has got a definite shape and a volume, and therefore, that is final set. So, that is the final set. So, it has got a definite shape and volume and it is final set. Followed by them is rigid solid gaining strength with time, and this process we call as hardening. So, it will gradually gain strength, it will become now hard. The solid is there, it was soft initially, not very strong, but with time then it will gain strength and will become stronger, that process we call as hardening. So, this is the physical changes in case of hydration. Well, peak of temperature occurs 6 to 7 hours after mixing the water, and final set generally this time corresponds to about 10 hours or so, not more than 10 hours, that is most of the code will specify. most of the code will specify not more than 10 hours. Now, if you look at hydration process, you can consider just a small portion of water like this, it is a water like this, and let us say this is my cement grain. Cement grain, as you know, it is a crushed product, it is grinded, therefore, it will not have a rounded shape, it will have some sort of irregular shape, as we can see. So, it will have some sort of irregular shape. I can idealize this as a circle, something like this, right. So, cement shape was something like this, I idealize it to a circle. Now, let us say hydration proceeds. So, as the hydration proceeds, you see the product that would be formed, this portion has been actually, this cement has been consumed. The water comes from outside, the hydration proceeds means water has reacted with the cement from outer surface. Now, as we know, the product of hydration actually has got a density lower than, it has got a density, density of cement is 3.15, density of cement. We shall see that product and water has got 1, water density. Now, it has reacted and formed a product, this will have a density more than, less than 3.15, more than 1, somewhere in between. So, it occupies more volume than the volume that was occupied by cement. So, it occupies more volume than the volume that was occupied by the cement. So, therefore, you find that these spaces are also filled with solid. So, some water has reacted and the product has gone outside the periphery. The one which has remained within the original boundary, we call it as inner product, we call it as inner product, we call it as inner product. So, inner product is that product which is produced within the original grain boundary. Inner product is the hydration product which is produced within the original grain boundary. Let me repeat, cement has got a specific gravity of 3.15, water has got a specific gravity of 1, the product form has a specific gravity somewhat less than 3.15, smaller than 3.15, but more than 1. So, the new solid that is formed occupies more volume than the original volume of the cement. So, some product will be produced within that zone where original cement was there and water has entered and produced the hydration product, that product we call as inner product, and some product will be formed outside this and we call it outer product. Now, outer product obviously will have CHS, but it will also have some calcium hydroxide, it will have also calcium hydroxide. So, this ones precipitates are calcium hydroxides. So, these precipitates are calcium hydroxides. So, calcium hydroxides precipitates as because it is sparingly soluble, so it remains as a precipitate, non-sealing precipitate, non-sealing does not seal anything, non-sealing precipitate, whereas outer product CHS will be something like this, in the periphery of the original grain boundary. So, they will extend outside, right, and calcium hydroxides are precipitated outside, right, and unhydrated cement still remains inside. Let us say further reaction starts occurring. So, unhydrated cement now gets reduced and CHS outer product now increases to a large scale and you will still have this calcium hydroxide precipitates outside, but the black portion, if it has now stopped, the hydration has stopped, black portion represents blank space which are nothing but they will remain as pores, blank space which will remain as pores. So, black, they have become black from the blue water, finally, the water has evaporated and that has become pores, right. So, that is what we call as capillary pores, their sizes are large and therefore, we call them as capillary pores. So, this diagram explains you the process of hydration taking from an idealized cement particle, considering an idealized cement particle surrounded by water. Now, when these solids, as we have seen, all the solids that touch each other, at some corner or somewhere the solid skeleton is formed, touch each other, from the other side another particle, and so on, solid skeleton is formed. But remember, there will be large pores, large quantity of pores remaining at the initial stage, unless you have less water, very little water, less space to be filled by the solid products of hydration, and the continuous reaction progresses over a long period of time. We will look into this in some more details later on. Right. So, if I look at now the structural changes that occurs in case of hydration. On the y axis I have quantities of material, on the y axis I have quantities of material on this side, and x axis time. Initially it is in seconds and minutes, etc., etc. Initially it is in minutes, then it is in hours, then it is in days. Now, there are different products which are forming, as you can see. For example, this product, if you look at it, it is ettringite, this is ettringite. So, ettringite formation occurs. So, ettringite is the first one to be produced. It is produced, but if you remember, I said that it is not very stable. So, ettringite is the first one which is formed, but it is not very stable. So, after a certain period of time, it gets converted into monosulfate. It gets converted into monosulfate. So, this is the monosulfate, it gets converted into monosulfate. So, first thing that is formed is ettringite. CHS starts forming from about 1-2 hours, sorry, 7 to 8 hours. I mean, sorry, not 1, 2, 3 hours, etc., etc., not 6, 7 hours is here. So, it starts filling after some period of time, and then CHS would be produced in this manner. Different types of structural changes occurs from long fibers to the fibers form long fibers to short fibers formation will occur, and calcium hydroxide is also produced. So, this axis is volume or amount, and you can see calcium hydroxide volume or quantity increases with time as the hydration progresses. CHS long fiber initially formed, then the short fiber they will stabilize as short fiber. Calcium hydroxide is formed, but ettringite is formed in the beginning, it attains a peak, but then its concentration starts coming down because they get converted into monosulfate. It is not stable, get converted into monosulfate, and C4AF hydrates are formed there, which is not very important. So, we can see that the product those are formed is first is ettringite, then CHS, and ettringite gets converted into monosulfate. Calcium hydroxide produces together with the CHS, and monosulfate concentration increases. Simultaneously, volume of pores will go on reducing. Initially, most of large quantity will be water, and this will go on reducing, because these solids will occupy the spaces that was originally filled by water. So, dormant period, as I mentioned, chemically dormant period is actually ettringite reaction. Setting occurs when CHS starts forming, right, and then hardening is this period of time in days. Setting is in hours, hardening is days. And if we go back to the same structure, initially it was something like this, particles and water. Next stage, at this stage between dormant stage and setting, the fibers of CHS, etc., has started forming. Precipitates of calcium hydroxide would have started coming out after that, and here the lot of these fibers would have formed, lot of solid would have formed, and lastly, as the hardened structure would look something like this, hardened structure would look something like this. So, this is the hydration process, and the structural changes that occurs in cement when it mixes with water. When it comes in contact with water, we have seen the chemical reaction, and physically how the hydration process occurs, that we have seen, and just now we have seen the with time how different products are formed, So, that is what the hydration process is. Well, the hardened phase structure, if we look from backscattered electron microscopy image, unhydrated phase, you can see that, you can see the unhydrated phase here, right, and pores are the black ones. In fact, these all are pores, because we have separated out by binary separation all the black ones from rest of the color. So, these are the structure of the pores by binary separation, and the gray color, the white one, is unhydrated cement. In fact, calcium hydroxide is also white, largely white color, and gray color is hydrated phase, that is your hydration product, etc., etc. Calcium hydroxide of course remains as precipitate surrounding aggregate, or summer they will remain as non-sealing precipitate. So, backscattered electron microscopy confirms the process that I was talking about. In fact, it is from this ideas of electron microscopy and backscattered electron microscopy, the process of hydration model that I showed actually has been developed based on this kind of ideas. For example, if you look at electron microscope, right, this is a possibly calcium hydroxide, the hydrated product would be something like this, unhydrated product might look something like this, right. So, now we have seen the structure, we can come to the bonding action. We will repeat, of course, bonding action we will just initiate today, but we will continue to do it in the next class again. You see, CHS gel has large specific surface, and it is of the order of 2 to 3 into 10 to the power 6 centimeter square per gram. I have not defined the specific surface as yet. We will actually tell you how to measure specific surface of cement. It is the surface area per unit mass. Of course, we measure it in certain manner by certain techniques. Now, specific surface of CHS gel is very, very high, and it is about, you can see that it is possibly about 1000 times more than that of cement, because it is 2 to 3 into 10 to the power 6 centimeter square, and where it is 2.2 into 10 to the power 3 to 4 into 10 to the power 3. So, this 10 to the power 3, this 10 to the power 6. So, order is 1000 times. So, therefore, particle sizes are colloidal size, very small particle size if you think in terms of particle. So, they are very fine sizes, and therefore, surface forces starts acting or dominating, surface forces start acting and dominating, and the surface forces which are intermolecular in nature of the order of around 7 MPa are responsible for cementing action of gel to gel. So, gel to gel cementing action is because of intermolecular forces, what is called van der Waals forces, we will come to that. So, intermolecular forces are those that act between stable molecules or between functional groups, between macromolecules or between molecules. So, they are called intermolecular forces. Within the molecule it is covalent electrovalent bonds, but between molecules there are certain intermolecular forces, and gel to gel bond attraction is intermolecular in nature. This is not chemical bond from gel to gel, because gel is CHS, another CHS, there is intermolecular forces between CHS gel system, right. So, bonding action of this intermolecular forces, they are generally weak, not chemical bond, not very strong. We have seen that it is about 7 MPa of the order of this, but actual bond could be possibly more than that. Well, cement to cement bond is because of this. Now, we will understand this a little bit more in the next class by by understanding the nature of this kind of intermolecular forces a little bit more. We will go into the fundamentals of this a little bit more, what causes these forces in material, and then we will follow it up for bonding action of cement. So, we will follow it up for bonding action. So, I think we should summarize it right now. We will summarize our discussion at this stage. The rest of the bonding we will discuss in the next class. Summarizing this for today's discussion would be, we have looked into structure of compounds, structure and hydration process, and somewhat we looked into the hydration product and the processes involved, and we have also introduced you bonding action, right. So, what we have looked therefore, we have first looked into structure of the cement compounds, and one thing we have identified that they are large anions with small cations. So, therefore, they are not stable and can stable, this crystalline structure is not stable, because packing density is not stable packing density. Therefore, like many others compounds or salts, they actually react with water or take water around the cation to form a kind of stable structure. Cement is of the similar kind, and that is why they react with water. Now, basic structure of the cement compounds come from silica structure SiO4, and that is why they absorb water. We have looked into the hydration process, and the product that is formed, that being very fine, surface forces dominate, and that is why you have bonding between gel to gel, which is not very strong, but somewhat strong. In the next class, we will look into this bonding action and more to the physical structure of the cement hydrates. Thank you.